Okay, we have a vector definition of angular momentum as I times the vector omega. Now what's a vector omega? Well, omega is going to be the rate of change of position, angular position, times u, where u is the unit vector along the axis of rotation. Okay, so u is the unit vector parallel to the axis of rotation in the direction determined by the right-hand rule. So if you have rotation around like this, the right-hand rule says that direction is here. There's no vector in the plane of rotation, no single vector that makes any sense as a vector that represents an angular velocity.
Wouldn't that be perpendicular to the axis of rotation?
No. Axis of rotation, if you're rotating here, your axis is here. Okay, the axis is what we mount the thing on, right? It's an axle, okay?
Mm-hmm.
And you don't always have an axle. A planet orbiting the sun has an angular momentum, okay? Which has to be constant because there's no force, no torque. The sun's always pulling toward itself. There's no torque about the sun. And we'll see how that works out, okay? Very interesting. Anyhow, you got an axis? Okay, so yeah, you have that. And then, of course, you can define the vector acceleration, angular acceleration, as the derivative of your angular velocity. And the derivative of this, u is a constant vector. It's a unit vector, vector magnitude 1, and you know that's what a unit vector is, right? Okay, vector magnitude 1, parallel to the axis. Same vector, okay? So there's your angular acceleration. Now your angular acceleration could actually be in the direction opposite your angular velocity because the derivative of d theta dt might be negative, okay? Or omega could be negative if theta prime is negative, okay? And then this could be either positive or negative depending what the second derivative is. Okay. So that's kind of the framework. Now, as we saw last time, if a particle hits a beam, let's say the beam's along this line, and hits the beam at a perpendicular, then the particle, because it could be regarded as having arrived at the collision by a path goes around the axis, okay? Path centered at the axis, circular path. It turns out that the particle would have mass at moment of inertia mr squared. Now that's what we established, okay? So I want to extend that a little bit. We've got a particle of mass m, and we want to know what its moment of inertia is with respect to this axis. Well, if there's a beam here, let's just pretend there's a beam or some extended object, and it's going to hit at this point, or even at this point, okay? Well, then the beam would be in this direction, and the velocity would not be perpendicular to the beam, okay? So that model wouldn't hold. The moment of inertia would not be mr squared. Matter of fact, if the axis was out here, this thing would have no moment of inertia because it's just going to hit the beam and on. That's going to have no effect on rotation. It might push the beam that way. It's not going to increase the rotation. I can pull on this beam as long as I want to in this direction, and it's not going to cause it to rotate. I can push on it in this direction as long as I want to. It's not going to cause it to rotate. Okay? As long as I'm pushing exactly the perpendicular, the beam in the direction toward the axis. Okay? Not going to cause rotation. Okay. So we say, well, if the beam was here, it wouldn't be hitting at a perpendicular. If the beam was here, it wouldn't be hitting a perpendicular, but there is a direction of the beam where this would be hitting at a perpendicular, right? And that direction is easily found. But there's the line of motion of the particle. And if we just make the direction something like this. Okay, imagine a beam in this direction. Then we can say that head in this direction such that this angle is 90 degrees, right angle. Then we can say that this is the R for which the moment of inertia is mr squared. Okay? Now there are ways I could describe this R. Okay? I could talk about extend this path and put the beam at this angle, and then it works, because that's going to be the effect of this collision with the beam wherever it hits the beam. I mean, that's going to be the moment of inertia of this. Okay? Okay? That's going to be the moment of inertia of this particle moving in this direction. The easiest way I can describe this is where R is the distance of the line of motion of the particle from the axis. Now that's a simple geometric concept, but since nobody teaches geometry, I've got to clarify it a little more. Okay? The distance of the line from the axis being the distance of closest approach, because that occurs when a vector from the axis to the line is at a right angle to the line. And it's a very simple proof from anybody who knows how to prove anything in geometry, which nobody does. Okay. Actually, probably do. But almost nobody does.
I don't think I did a single proof in the entire time I had geometry, but I did geometry in 8th grade.
There's some problems. Not your fault. I mean, you got a 5 on the AP calculus exam, but you know how to do a geometry proof. Not a reflection on you, but it's a terrible reflection on our education system. Okay, so, does that make any sense? Well, then there's this thing about the cross product. Something that I asked you to review or to learn in the first chapter of the text, but maybe I should talk about it a little bit. Okay? If I make this into a vector, then I can talk about the cross product of the velocity and the r vector. okay, or the cross product of a momentum and the r vector, okay? And the cross product I used U for unit vector before, but I'd specified it as a unit vector. That's no longer the case. I'm going to still want to use U because it's kind of traditional. And I don't want to use V because I'm using that for velocity. Okay? So cross product of vectors U and W and I'd better specify the order of the cross product because that matters. So I'll call it the cross product U cross W in the vectors, okay? The orientation is determined by the right-hand rule. Crossing V into W. And I'll say it quickly, but I'll give it a little more explanation. If V is in this direction and W is in this direction, you put your hand like this. Here's V. And then you turn it toward W and your thumb gives you the direction. If you did W cross V, your hand would be here and you'd have to turn it toward that direction, which means you better turn your hand over and it's down. Okay? It's fairly simple. And you can think of how you drive a screw. Okay? If you drive a screw, you drive it counterclockwise. You drive it this way and it goes into the
Not roadblocks.
board or whatever you're driving it into, okay? Make sense? Turn it this way, come up with the board. Another way to see it. This, or this, or this. And you can read about it. You gotta play around with it, make sure it makes sense. But if you do that, you'll be okay with it. Okay, you turn by the right-hand rule. And having magnitude equal to the magnitude of V times the magnitude of W times the sine of the angle, okay? Between V and W. Now let's see how that applies to the situation. Okay, we had again a particle like so. Okay. That's not a good direction. Maybe that was a better direction. I can't see from this angle. There's your right angle, so here's your R vector. Okay. Now, if this thing It's there, its moment of inertia
I love
is,
her so much, but I always turn mine out.
Hey, I don't know what.
they're moving. Okay. If the mass hits here, okay, there's a mass, m with velocity v, its moment of inertia is going to be mr squared. Okay? Which means its angular velocity is going to be, its angular momentum, okay, is going to be I omega. Okay? Well, that would be mr squared times the angular velocity it would have if it was moving around a circle of this radius. Okay?
You say it one more time?
Now you're going to have to look at the video from last time. I'll say it one more time, but to digest it, you need to have seen the video. Can't assume that you didn't. You got to keep moving, okay? But just as I demonstrated over there, if this thing is moving at velocity v around a circle of this radius, okay, then it has an angular momentum equal to equal to I omega, where omega is the angular velocity around here. Well, the angular velocity around here, and of course, you know, the long set of simple problems I gave you establishes it. The angular velocity around here is v over r. So it's mr squared times v over r, and that's your angular momentum, okay? Now, I'm just saying that, but I'll flesh that out with some questions, okay? Because this is not a simple concept, one of the harder ones we see. We've got to have the building blocks. So, as it turns out, just deciding how I want to write it. I could, let's say P, but I'll just use MV, okay? It's MV cross R, and I think I've got that backwards, it's R cross MV, okay? Because MV cross, no, that's right, it's MV cross R, okay. Torque is R cross F. Something is bothering me about that. But the angular momentum would tend to increase the angular velocity in this direction, which is this one. So, yeah, that's, and MV's in this direction. Oh, no, the MV cross R would be like this, so. It's not being careful with my visualization. It's R cross MV. And there are various symbols that get used. L is one that's used kind of frequently for angular momentum. Okay, so magnitude of L the magnitude of R cross MV, that's the magnitude of R times the magnitude of MV times the sine of theta. Where theta is the angle between R and MV. Well, that's a right angle, isn't it? magnitude of L is just R times MV. But V is omega R, which is the omega R we get if we assume the thing was hitting with that velocity, moving in this circle. This radius of the circle be R, velocity mv, which is mr squared omega squared something's wrong. Yeah, actually something's wrong here, that's not coming out right.
Shouldn't it just be mr squared omega?
Well, first place, omega is V divided by R. But there's a problem with that. So something's wrong. Just something stupid, I've seen it back, so I'm gonna stop here and clarify it.